Before we look at function slope or linearization of a function, it's appropriate that we do a brief review of our function notation. We're going to look at function notation and need to be careful with it in preparation for limits. A function f on the real line is a mapping from the set of real numbers into the set of real numbers such that each input has a unique output. It is traditional to use x to label the inputs and y to label the output, and to write y equals f of x to indicate that y is the result of plugging x into the function f. We don't always have to follow this tradition. We could plug t in and get out s and so on. We could use other letters, and we will from time to time. But for the moment, we'll assume x is being plugged into the function and y is the output. Let's do some examples with function notation. A simple exercise is suppose f of x is x squared plus 5, and write out in as simple a form as possible what happens if x is 3 or minus 3, square root of 5, or something more complicated. If x is 3, then f of 3 is 3 squared plus 5, and we simplify that to 14. If x is minus 3, we get the same result. If we plug in the square root of 5, we square the square root of 5 and then add 5. In our function, at each stage, whatever is inside the parentheses in the function notation, such as 3 minus z, replaces the x in the function notation. So f of 3 minus z is 3 minus z squared plus 5, and we have to do some algebra. If we plug in a plus b, we do some algebra and get this. We might plug in x naught plus h, in which case we square x naught plus h and add 5 and do some algebra. If we plug in g of theta into my function f, where g of theta here is sine theta, then we square sine theta and add 5. Again, f of x, that notation means that everywhere you see x in the expression, you're going to replace that x by whatever it is f of. All right, f of 3, replace everything by 3. On the other hand, we're also going to need to think about inverse functions. So let's look at this notation. If f of x is x squared plus 5, we can restrict the domain of f of x so that the function is invertible and give an inverse function for f of x. In this case, if y is x squared plus 5, then y minus 5 is x squared. Our goal, now that we've been given the if you stick in x, you get out y, our goal now is to switch that so that if you give me y, we can find x. If y minus 5 is x squared, if we know what y is, can we work out what x is? Almost. The function f of x here maps a positive real number r and its negative to the same thing. So if we restrict the domain of f of x to be non-negative real numbers, we restrict it to the interval from 0 to infinity, then we can avoid the problem of having the inverse relation give us two outputs. And so we can define g of x to be the positive square root of x minus 5. This function g of x is the inverse function under the added assumption that we are plugging only non-negative numbers into f of x, and so we're expecting to get only non-negative numbers out of g of x. Under this assumption, f and g have reverse operations in some sense. If you plug x into g and then into f, you get x back. If you plug x into f and then into g, you get x back. F and g undo the operations of each other. Now, where we're headed with all this is that lines are the simple and easiest function to use, and so we're going to often try to replace a function near a particular point P by a straight line, by a linear function, say L of x equals mx plus b, where this linear function L of x closely approximates my function near the point P. If we know the slope of the function f of x at P, this will be easy to do. We simply write out the equation for the line through this point with that slope, and that will be our linearization. That will be the topic of the next lesson.